Hi there, this is Dr. John, your physics and math professor, coming to you with another circular motion problem. Actually, this is two problems. I've wrapped them into one, a car on a flat road and a car on a banked road. What I mean by that is this. Here we have the car going up the road like this in the direction of the arrow, and then it's turning until it's going in this direction here. And the radius that it turns around, we call it the radius of curvature. Just think of a string being attached here, and you would move that string like this. So this is like the center of the circle of this curve. It's just a partial circle, but it's still radius of curvature of the circle. It could be a very long curvature. It could be like, several hundred meters or a kilometer. It could be shorter as well. So what you would have here, obviously, if you've ever driven in a car before, as we all have, you would realize as you're turning this curve, you feel a pressure and the car feels a pressure to go off into the bushes over there. And something has to keep you on the road. Something has to keep you going this way. And there's two different things that could do that. One is you could have a friction between the tires and the car. And the other is the car could go on a bank. The road itself could be banked. What I mean by that is that this road here could be up like this. So the far side could be banked up this way and banked up this way. And they tend to do that to make it safe to go around there. Even if the road is icy and you don't have much friction, you'll still have the bank to keep you on the road. And your car will experience a sense, a force that it's being pushed outward, or you're going to have to create an inward acceleration, and that inward acceleration is going to be equal to v squared over r to go around the curve. Let me just show you and explain what I mean by that. Let's say you're going straight ahead here, just like indicated in this arrow here. To be able to turn this way, you're going to have to make a slight acceleration in that direction. And then you're going to be going in a slightly, I would draw this arrow up here, but I'm going to get in the way of my writing here. So I'm just going to draw this arrow over here. And then you're going to be going in this direction. See, this direction over here. And then you're going to have to make another turn a little bit in that direction. You're going to have to constantly make a pull or an acceleration to the left until eventually, obviously, you're going this way. So your acceleration, we can do this from geometry. I'm not going to do the details of this here. Your acceleration that you're going to have to create is going to be directly toward the center of this radius, and it's going to have to be equal to v squared, your velocity that you're traveling, v squared over r, the radius of curvature, which means something is going to have to give you a force equal to mv squared over r to make you turn in this direction. This is called the centripetal force, centripetal or centripetal acceleration. In the olden days, they used to refer to this as also the centrifugal acceleration, which meant that there's a force as you go around the corner here, there's a force that's pushing you off into the bushes. It's an apparent force. It's like a fake force of gravity. Just like when you're in an elevator and you're being accelerated upward, you feel like you're being pushed downward. That's like a fake gravity that the elevator is creating for you, an artificial gravity due to acceleration. This is the same. You're accelerating inward, but your car feels a force, an extra gravity, if you want to so say, off into the bushes there as well, which we call the centrifugal, meaning it's being centrifuged away from the center. There are centrifuges that spin things around and separate things according to density and mass. And so this would be a similar, we don't use that word as much today, but the value of that, the centrifugal, is exactly the same as the centripetal, or the one that you're pedaling toward the middle. You're constantly pedaling toward the middle, the centripetal acceleration, which we call FC, is equal to the mass of the car and this thing right here. So this car is going to need to accelerate in that direction. Something's going to have to cause it to do that. We're going to look at these two different examples and see what might do that. Give me a second to just move some things. So here I've come back. I've erased these equations here for the centripetal acceleration and centripetal force, and I put them right down here. So they're handy for us to use in the future. And then I've redrawn here the flat road illustration of all the different forces that might be acting on this car. We obviously have the normal force going up, the force of gravity going down. Some people just call this the big N. Some people call it F and N, a little f with an F with a little n, because they're all forces. I'm just going to put it N just so we don't have too many letter F's here around here. And this is just called mg. Sometimes the force of gravity, Fg. And we would have this thing here would be the acceleration you're going to need to create or to do to make it stay on the road. You're going to need to do that. How do you do that? Well, there's not enough arrows on here yet. There's one more thing, and that is these tires are going to have to create a friction on the road. They're going to have to create a force of friction in this direction. Now, I know that looks like this is a force and this is a force here. But what we have to be really careful of here is to realize that this thing here is what you need to create, and this is what creates this. So when some people create this diagram, they'll actually put this FC in this direction, being the centrifugal force, and then the force of friction is going to have to be equal to this, and they're balanced. Because what you can do then is you can say, let's look at this thing here now with a sort of a new coordinate system. Normally we have the X coordinate system and the Y coordinate system. Those are completely separate from each other. And here what we have is we have the coordinate system coming out from the page, which is this one up and down here. That's the one thing here that has forces acting on it. And the other one is sort of this circular coordinate system here. And we've just drawn a cutout, one little piece from that right here. We're just seeing the car, the forces on that. So you could look at this, the centripetal acceleration, the centripetal force, or we could use the centrifugal force. Right now, just for this diagram, I'm just going to introduce you to that idea and just put this. But it's very important to realize that it's not like this is a force and this is a force and they're all acting in that direction. You have to add them up. What this means here very simply is this force here, the force of friction, I made it red because it's painful. The force of friction has to equal or create this FC here. It's the only one that can actually do that. And how do we calculate the force of friction? Well, we probably have done this in a number of other problems. The force of friction in equations like this is equal to the normal force times the coefficient of friction. Let me just talk about coefficient of friction for just a second. So for a coefficient of friction, you have the idea that the rubber on the tires is going to be constantly contacting the road. As you're driving, the tires actually, the outside of the tires are rolling at the same speed that you're driving. In other words, they're constantly touching the road. They're not slipping on the road. It might feel like they are. You'll have two different types of coefficients of friction, often labeled with this letter mu. It's like an M with a longer stick on the left side. So you could have a mu kinetic, which would mean that your tires aren't actually touching the road constantly, they're slipping. So if you're on ice and you hit the brakes, your tires will lock and your car will start skidding, which is very, very bad for your friction. This is called the kinetic, which means moving or slipping or sliding. And then there's another one, which would be the coefficient of static friction. The coefficient of kinetic friction, that is the friction where you're slipping, would be less than this because you don't have as much grip. So I'm just going to write that in here. Mu K is less than mu S in practically all cases. In other words, you do not want your tires to slip. So touch your brakes gently or make sure you don't go too fast around the curves so you slip. We're not actually worried about whether this is static or kinetic. We're going to assume it's static friction and we're just going to use the letter mu. We're not going to put a little sub letter on that. I just wanted to mention that to you in case you've been facing that in your assignments. So now let's take a look at this here again. That means, as I said here, the centripetal force is created by something. It's created by the force of friction in the inward direction. So that means these two have to be equal. Let's write out what those would be. We've already said that the force of friction is equal to N mu. So that's N times mu. That would be equal to what? Well, we had this before, mv squared over r. In this case of a flat road, the normal force going up and up has to be equal to mg because the road's not buckling, it's not going down as I mentioned before. So N is have to equal to mg, which we could replace right in here. Let me do that. mg mu is equal to m v squared over r. I replace this m with these things right here. All right? Now notice in this equation here, you have an m here and an m here. We can cancel both of those. And then we take this g and move it over to this side and put it under there. So I'm going to rewrite that up here a little bit. So this means mu, the coefficient of friction between the tires and the road, is going to be equal to v squared over rg. Notice this g, I moved down under there, so it's rg. So this would tell you the faster you go, the more coefficient of friction you need, the bigger the curve, that is, it's going longer like this, the less co-friction you need. And of course, gravity has a part to play in that as well. Let's check the units out on this and see if they work for mu. Meters per second on the top, meters per second, but they're both squared, so I'm going to square them both. And the bottom, it's g, which is meters per second squared. We multiply by another meters, so it's meters squared per second squared. So this, notice, meters squared per second squared, meters squared per second squared, same units in the top and the bottom. So that means mu is unitless. Everything else here has units. R is in meters, this is in meters per second squared. The normal force is in newtons, so everything has units, but mu does not have any units. It's completely unitless. It's just a number. And that's very important because if you notice here that the force of friction is equal to the normal force, which is already a force, it's already in newtons, times mu. If mu had newtons, then you would actually have to change the units in these two forces, which you can't do. So it's just simply a number. Really important to remember that when you write the answer, the mu would just be equal to 0.3 or whatever the answer is. And mu here, in most cases, is between 0 and 1. For things like ice, it might be 0.1. For things like this, it might be 0.8, 0.9, something like that. It might be much higher. Gravel, it would be much higher. So you'll always be looking for something between there. If it's not, then you probably made a math mistake somewhere. Let's take this answer and write it under here, and then we'll erase a couple of things here and be ready for the second part of this problem. Okay, I'm back. I have redrawn this banked curve problem right over here. Just sort of copy this here, that's the angle theta. And I've tried to put some of the forces in there that we're going to be dealing with here. And again, let me just explain where these come from. First of all, there's the normal force coming straight out from the road. The normal force always, the word normal actually in math or in physics like this actually means perpendicular. Many years ago, they used to have, people would go to school to learn how to be a teacher in Canada, and they would be called normal school. The word normal can be used in many different ways. Here it does not mean what you might think it means. It means perpendicular. So whatever the surface is, it's at 90 degrees to the surface coming straight out, because that was the surface would push up on the car. Mg is the, notice down at an angle, that's the mass of the car influenced by gravity. That's the force of gravity. And then this here, I put this in double arrows so that we'll see it clearly. There has to be a force that pulls this and creates this force, this centripetal, this centripetal force. Now also the car will feel a force pushing to the outside, which we call the centrifugal. We could push that, we could make that arrow in this direction, but just not to put too many arrows in there. I'm going to need that idea later for another video. So this force here is not actually a force that is causing something. This is a force that is the result of something. This is the sort of the resultant force. I wrote it over here, mv squared over r. That's how much force you're going to need. Something else is going to have to create this force. In this case, you can simply sort of see on this that force partly is going to be created by the force of gravity. And let me just break this down for you and take this here just to help to make this a little simpler. I find this very useful. If you do, then use this method. If you don't, that's fine. So what I do is I'll take this and I'll take this whole thing and sort of flatten it out. So I'll look at it not like this, but tilt my head a little bit and see what there might be. So take a look here at the force of gravity. It's now going to be going in this direction. This is now mg. It's going at an angle, but what angle is it? Let's think about this for a second. I'm going to make some dashed lines here. This would be the normal going downward. What is this new angle here? Alpha. Well, just think about this for a second. What if we flattened out the road and made theta smaller and smaller? What would happen to the angle alpha? Obviously, gravity would become more and more perpendicular or identical to this perpendicular. It would be the same as this. That means this angle theta is the same as this angle alpha. So I'm just going to rewrite it that way. This is also the angle theta, same angle as we have over here. So notice how there's going to be components to this. I'm going to try to break this up into components for you. One is going to be this component here, and one is going to be this component here. And I'll just draw this over here again so we can see this a little bigger. So here's a triangle like this, like there. And notice this angle theta up here. And we already have mg. mg is this one over here. And then we have this, you notice, is the opposite, and this is the adjacent, if you remember using your triangles. So this one over here, since this is the adjacent, that would mean the cosine of this angle is going to be equal to this value here, this y value, y divided by mg. Which means we could put mg over here, and we could say y is equal to mg, y is equal to mg cos theta. There we go. And this one over here, I'll make that in pink. This would be the x value of the component of this, which would be mg sine theta, because it's the opposite over the hypotenuse is the angle. So this is the hypotenuse over here, so it would be this angle, this side x over mg is equal to sine theta. I move the mg to this side and I get this solved like this. So now I have these two components that are contributing to the car from gravity. And I'm just going to write them in here. So here I've rewritten this. The x component, or the component that lies like this, parallel to the surface, is mg sine theta. The perpendicular component is mg cos theta. I don't need this here anymore. Let me erase this. Now these two things, this one is going to actually pull the car in that direction, down the slope. If you can see that, notice it's going to actually pull the car down the slope. The other one is going to oppose the normal force. Since we don't have friction in this case, we're not concerned about this component at all, because the normal force is balanced with that. So all we really need is this force over here, this one that's pulling this way. Now if we notice here also, there's another force acting, and that is this thing here, the centripetal acceleration, or the centripetal force. It's actually a force that is the result of something else. So it's going to have to be equal to something else. And in the previous case, it was going off at an angle like that. Or what angle would that be? Well, if you take a look at this very carefully, what angle would this be compared to the angle of the inclination here on the road? Well, if we look at this here like this, you'll notice very, very quickly here that this angle theta is the same as this angle up there. In other words, again, if you went flat here, the centripetal acceleration or force would be acting directly that way. As you increase that angle, the angle of inclination, it's going to be acting at a higher and higher angle until it hits 90 degrees. So this is the same angle there. Now we can break this component. This also is FC here. I'm going to redraw this over here. I have redrawn this force over here, going at this angle here, this angle theta, to the surface of the road. And that angle we've gotten from this original angle. And then we're going to have an opposite component. This opposite component is going to be this one right here, straight up from the road. So it's, in other words, it's a normal, which would be the same as this one over here going down. We don't need that one. All we need is this one over here. This one over here. So that would be this one right here. Now, how would we find that? X. If you remember from trigonometry, that the cosine of theta is equal to the adjacent, which is x, divided by the hypotenuse, which is FC. Now what we want to do is we want to solve for x, so we'll multiply this by FC, and we'll have that. X is equal to this. X is equal to, there we go, FC cosine theta. That's this component right here. I'm just going to write that up here. That's that component there. I didn't want to get too messy and scribble things in too small. Now I can erase this, and we can show what the resultant is here. Notice that this force right here, which acts in this direction here, has to be, it is the component of the way over here, the centripetal force. It's the component that acts in this direction, that acts in the direction of the road, of the bank of the road, like flat like this. It's going to have to be caused by this, which is the component of gravity that's in the same direction. The other one is perpendicular to the surface. So in other words, this mg sine theta causes this. Let me write those things out here because those have to be equal in magnitude. Mg sine theta causes, and that therefore is equal to this, Fc cos theta. Now we want to solve somehow for the angle here. So let's take and divide both sides by cosine theta, like that. And then we're going to have a tangent theta over here. So this is tangent theta is equal to Fc. And then we have these other things over here. Let's move the m and the g over this side, over mg. Now we have tangent theta equal to something. Let me just erase something here. What is Fc? We had this before. It's mv squared over r. So this side is m v squared over r. And what else do we have in the denominator here? Mg. Like that. The m's can cancel, and we have v squared over rg. So tangent theta is equal to v squared over rg. Just like that. If you notice over here, the coefficient of friction on a flat road is v squared over rg. The tangent of the angle here of the sloped road, the banked road, is also V squared over RG. I'm going to write that up there. You have just erased a couple of things just to review. We have the flat road, and we have this force that needs to be pushed in this direction. We need a force in this direction called m v squared over an r. We need an acceleration v squared over r in this direction. How is that caused? By one, here, if you have friction, it's caused by the coefficient of friction and the tires. As you're turning the tires, the friction there will pull your car in this direction, hence causing the acceleration. That's the coefficient of friction you need. Or if you have no friction, let's say it's a real slippery road and you have a banked road, then the one component, this component, notice, downward, there's going to be a component in this direction as well here. If you divide this up, there's going to be a component in this direction here that's taking you down the bank, hence is going to be pulling you this way and accelerating you. Of course, if you went really slowly on that road, you might actually slide down the bank. So you're going to have to keep up at least a minimum speed to keep you on the road. But this is sort of like the ideal, perfect bank for a certain speed. So when road construction people would look at things, they would say, you're supposed to drive 50 miles per hour or 60 or 100 kilometers per hour around this curve. So we're going to make the embankment so even if it's icy and you're going roughly that speed, you're going to stay on the road. They might make it for a little lower speed because they don't want to make you race around there when it's icy. That would be the way that they would think about this embankment here. I hope that helped you just to realize that these things are extremely similar. If you can do this problem, you can do a lot of problems with circular motion, with embanked, and with cars on the road. I hope this helped. If it did, like and subscribe, and I will see you in the next video. Bye-bye.